quality engineer. My current position now is as an engineering consultant. And so this is perfect topic for me to present, something that I'm really familiar with, and I think I can provide some good help for you. So let's go ahead and begin the presentation. And I'll start the slideshow. So the first thing I'm going to do is ask that you look on your control panel for GoToWebinar, and you should see a hand that you can press, and that tells me that I'm coming through to you with the audio and video. So please press that hand. Susan, thank you. Rob, Joe, okay, Greg, thanks a lot, guys. That gives me a good sampling. I know it's working. From time to time, I'll come back and ask you to just give me some hands up so that I know that we're continuing to operate here, especially the voice over internet protocol sometimes goes a little bit wacky. It's interesting that I've got this graphic in here because it turns out just on the other side of my home office window, Staddy's having been out of the office now since March and working at home. And I've got two distance learners, two of my grandchildren, just on the other side of the wall. So if you hear a few chatters coming through, that's the reason. Hopefully they won't get too frisky like these two people here, but that's kind of symbolic of stuff that can happen. You know, you're trying to get your experiment done and somebody throws a curveball in on you. Usually it's Mother Nature, you know, with some kind of issue like humidity or temperature, or some mistake is made. There's lots of things that happen that cause bad data. And sometimes it's a special cause like this fellow here, but other times it could be due to other issues with how you do the modeling, such as using transformations. So again, welcome everyone. I do have attendees on mute. It turns out that we ran into a little technical issue on Sherry's side to try to get in and cover the chat line. So then what I'm going to suggest is that you write down any questions that you come across, and if it relates to a certain slide number, make a note of that, or if it's just a general question, that's fine. And you can send that to mark@steadies.com. So anything related to the presentation, feel free to send me an email afterwards and I'll get right on it. Just so you know, in general, if you have questions about our software, DOE, things like that, we also have a more general line called stathelp@steadies.com. And that is a good email to send just any general question you have about Design Expert in particular, and how it can do design of experiments for you. Also, the presentation is posted and a recording will follow. So if you want to go back and fill in on some of the things, go back to the recording, and that should be helpful for this issue of how to detect and overcome bad data. So just one more time, then I'll ask you to press that raise hand, just so that I know you're still with me. Okay, thanks very much. I've got people from Alan to Yun that have raised their hands. We've got a good audience today. Thank you very much for attending. Okay, so I put the hands back down and we'll press ahead. So our agenda today, I'm going to get to in just a minute, but it's kind of interesting because literally a few minutes ago, this morning, I got this question. Hello, Mark. Could I please have your opinion on this? I am a beginner on DOE. I have an outlier in my model, and this is showing up in the diagnostics from DX, and it's residual versus run, which is one of my favorite charts. I always look at this because stuff is always happening. So what would someone do? Is the model still valid? Thanks for your help. Well, of course, you know, I had to give the standard answer that we always give as a stat consultant, and that is, it depends. Because what I sent back to her just a few minutes ago was there some kind of a special cause, some kind of breakdown in the equipment or a bad solution for this particular mixture, you know, or could there have been a series of runs where things were going off, because I said it seems like maybe there's a series that are unusually low, but definitely this gets your attention when you have a point outside of the red line. So this is exactly the sort of issue that we're talking about, and it's a very timely question. Of course, I said you've got to send me your data in DX format, because I can't just answer the question without looking at the actual data. So that might be the standard answer. It depends. Send me the data. So stuff is happening all the time. And interestingly enough, yesterday here in Minnesota, guess what? We got an early snowstorm, and it was, I think, probably about 8 inches. And that was, a new record for all the time that they've been keeping track of records here in Twin Cities of over 100 years. So what are we going to do? For this one, I have an answer. New snowblower. I bought it 2 weeks ago. So I'm a pretty happy camper, because I just got right out there with this new Toro, which is an electric, and it worked like crazy. So you've got to be prepared. Stuff is going to happen. And so I'll show you some different issues that come up to start with. Then we break down into two types of things that can happen. One is that you have a false alarm. And an example I have is from George Box on Bearing Life. And it's really what we call a type 1 error, in that it's an alarm, but it's false. But another error that can occur is a lot more difficult. Failure to detect an outlier. This is an issue of power, and this is a type 2 error. And I have another example here where you'd think there is an outlier, but you actually don't detect it, and then your whole design gets messed up because of it. So we'll talk about two different scenarios here as we work through here: the false alarm and the failure to detect, and then we'll finish up with conclusion. And I should be able to finish this up, within the hour, and possibly I could take some questions at the end where people could raise their hand and go on mic. We'll see how that goes. But I do again suggest that you write down questions and be prepared to email those to me afterwards. So let's talk about thorny issues. Stuff is always happening. And number one anecdote that I've got to present is this pig's eye treatment plant case, where they kept only the low results. So it turned out that this was related to me by my father, who's a master's civil engineer. And back in the day, he came into this wastewater treatment plant, which is called pig's eye treatment, because of the original founder of St. Paul, Minnesota, settled there in this area of the Mississippi River. And that turned out to be a good place to do the wastewater treatment. And so he came in, and he was told that he needed to throw in tons of flocculant. Tons of flocculant needed to be added to the effluent to precipitate, the waste out of it. And he really questioned that. So he got in contact with a fellow named George Box. Now you got to keep in mind that this was back in the 1960s. And at that time, Box had emigrated to Madison, Wisconsin, and set up camp there, and was a tremendous resource. And George Box said, you ought to do a design of experiments. And it turned out, when he did the design of experiments, that there was no significant improvement to the wastewater treatment because of the flocculant. And the reason was, when he went back and looked at the chief engineer's data, the engineer would always throw out the high data. And this is called a confirmation bias. It's very common and very diabolical. Another confirmation bias occurred with the cold fusion situation with Pons and Stanley way back, I think probably 20 or 30 years ago now. You may recall that they thought they saw evidence of cold fusion, but here again, they were biasing the results by keeping only the high results. So this bias is something to really watch out for and be very careful about. so that you can, avoid these false positives. Another side of it then is overlooking actual outliers and missing something. And this could be because you've got too much noise in the system to be able to see the real effects, drawing, false conclusions. And this could be, something that could really prevent you from a great opportunity. And one example is ozone hole that they thought they were seeing, and they were missing out because the instruments were not following it properly. And another example of something that is an outlier, but it turned out to be a great discovery, was the 3M Post-it notes. So there's lots of things that can go off one way or the other. Stuff happens all the time. One of the first and foremost issues that create outliers are just simply typographical errors. So I always suggest that you type the data from the top and proof it from the bottom. I've gotten in bad trouble a few times by not being careful to check my entry. So that would be the first thing to check. Secondly would be breakdowns in equipment. I remember one time I did a molding process, and I had this sheet of ABS plastic that was going to be going up and down between 2 radiant heaters, and one of the radiant heater bands broke down. That sort of thing can happen. Operators make mistakes. I got this email some years back. Mark, regarding the odd result, we had an accident in the lab and one of the techs caught on fire. That was fairly alarming. So that would be a special cause. Sampling, that's something to be really careful about. Is the sample representative of the process? Measurements, very common that somehow something goes wrong with your measurement. And then there's the unknown lurking variables, something that happens only intermittently. There was a famous case that I had in my MBA class where a locomotive would come by at a certain time of the day. It was generating, a lot of smoke. It would come in through the ventilators, and then they would get particles in the textiles they were producing. That was a lurking variable eventually they discovered. And has stuff ever happened to you? So I'm going to take a show of hands. Have you ever run across some issue when you're doing an experiment that threw your results off? If that's the case, press your hand. And I think most of you are going to press your hand at this point because that's why you're in this talk. If it hasn't happened to you, then you're not really looking too close, I'm afraid. And maybe you need to have better diagnostics. Okay, so I'm putting the hands back down. That was a softball question. So here are the type of things that can happen kind of laid out in something called a truth test. Okay, so let's say that we know the absolute truth. So we're able to play the role of Almighty. And we know that there aren't any outliers, that the process is stable. It's running out just like it naturally should. And if you think there are no outliers, then it's all okay. But if you think you've detected an outlier and there really isn't an outlier, that would be a false alarm. And so that would be an example of a type 1 error. Then on the other side is that something did happen and it did throw the runoff. There was a physical cause for it. You recognize that, by diagnosing it properly, that's okay. But if you don't have good diagnostic tools and you fail to detect that, it could throw the whole experiment off. And this would be a bad mistake, or what we call a type 2 error, this failure to detect. So I do have 2 case studies that illustrate these 2 error types. So let's talk about the first type of problem where there's a false alarm, a type 1 error. And this gets us to this case by George Box. And George Box had a protege, somebody who came to Madison to train at the Quality Institute. And his name was Christer Hellstrand. I may have this spelling a little off. And the company he was with was SKF in Sweden. And their company was close to bankruptcy in the 1970s because the Japanese had come up with a new bearing that was much better and cheaper than the bearing that they had invented at SKF back in the early 1900s that was an all metal bearing. Well, one of the things that they saw was the Japanese were making use of plastics, and so they decided they would try a different design for the cage of the bearings that would be plastic. And so they had this existing bearing that's down here in the lower right corner. And one of the things they were looking at was the effect of going from metal to plastic, which is actually in this diagram factor C. Factor A was to change the kiss of the bearing to the cage, which is called oscillation. And so they were changing that, from the current level to a new level. Okay, so the low levels are existing and the high levels, which are labeled plus, are the new. And we're going from the front to the back on C. Then the other factor was a heat treatment that was going from low to high. And their goal was to double the life. However, when they did the one factor at a time approach, it didn't work because they got improvements, but they didn't get doubling for any of these attributes. And so it just didn't work. But what Hellstrand found out from Box is that you can do something called multi-factor testing by doing a 2-level design with 3 factors and doing all 8 combinations. And he was able to see this huge interaction over here on the right-hand side. Now, here's the weird part of it. If you put this data into Design Expert, for example, and you analyze it, these would be taken out as outliers. They're actually statistical outliers. And so you would completely miss out on this whole opportunity of doing the multi-factor testing. So what I'm going to do is I'm going to bring this up on Design Expert. And one of the first things that we'll notice is that there's a discrepancy from the near zero line and the half normal line with the origin of 0, because normally these points should line up. And that's going to be one of the first things that a person who's very astute would notice. And I want to give you that tip that when these near zero effects do not align with the origin, you should proceed with caution. And then we're going to see on the residual versus run, similar to what I showed you from the client that just emailed me this morning, an outlier, but there's actually 2 outliers. They're just barely touching the lines, but they definitely stand out. And those are the 2 big effects. But we'll see with Design Expert that there's a way to save this if you're smart enough to do the diagnostics and look at the Box-Cox plot. You're going to notice that where we currently are located at with no transformation, all the data to the power of 1 is outside of this box. And this is like, a hockey net, right? We want to be in the goal. We don't want to be out of the goal. So it turns out that if we set at this lambda 0, which is the limiting case for a log, either base 10 or natural, that will save, this whole data set. So what I'll do is I'll bring up Design Expert now and show you how easy it is to set up this design. I'll rebuild it, model the results, and analyze them, including diagnostics, which in this case is going to be vital. And the key is going to be this Box-Cox plot. So let's take a look at this. I'll tab over and I'll open up Design Expert. So here's Design Expert, and I've got this bearings case teed up. So now I have showing the design layout. And since I've been blabbering on for a bit of time here, I think it's National Blabber Day. So it's a perfect time for me just to talk about things. But before I go any further, press that raise hand key if you see this design layout. And it should be a layout with different factors and different, great, okay. I've got a good sampling of results, thanks all. So how do we build this design up? Most of you probably are familiar with this, but some of you attending are new. So let's take a look at how this would be built up. It's very simple. Any of the full factorial, standard designs are going to be on this white diagonal. And I would recommend normally going for more than just 3 factors. certainly with 8 runs, you might consider going to 4 factors and just doing a screening design, which are the yellow designs. My favorite design was the 5-factor design, but doing a half fraction of it, just simply because 16 runs is going to be a lot more powerful than only 8 runs. However, there's such tremendous differences here caused by these huge factor changes that only 8 runs is sufficient to provide power to see the result. And the power is already proved because the results are significant. But normally I would advise, as you build up these designs, putting in your names. These are categoric factors. However, this particular factor here is actually a factor that would have a number associated with it, only for confidentiality reasons. In fact, both these first two are numeric factors, but the company didn't reveal exactly what those levels were. So we'll just keep them disguised as categoric. So really the only true categoric is the cage, the 2 different materials that are being used. But normally I would do the power calculation and then check and see what your power is. But it turned out that there was sufficient power. So let's go ahead and open up this file. And what I have here is actually the same results in 2 columns because I want to show you doing it as is and then reanalyzing using a transformation. And this particular data is laid out in standard order, but I hope and I trust, given box directed Hellstrand, that this was actually done in a randomized plan, but I don't know what that original randomized run order was. So I just have these sorted, by standard. And you can see, the big increase if I sort this, and you can see the big increase, just by graphing, how it's increasing, tremendously, with these factors. What we don't know at this point is, is it a main effect or an interaction? However, when you look at the cube plot, obviously it must be an interaction because of the upper right corner being so high. But we'll find out in just a minute because what Design Expert does is it gives you a very quick view of whether any effects are standing out by doing this half normal plot where the big effects are off to the right. And it's already preset in the newer versions with a line that should be pretty good in terms of lining out the near zero effects. But mind that gap here between the 0 and the first insignificant effect, and then mind this other gap, to where there are probably significant effects. And these are the ones we're going to pick. And these other ones will be in the error pool. But again, there's something a little bit flaky about this. So at first glance, this looks pretty promising. And we see, good p-values. Fit statistics, not too bad. But then here's where things get really off. And actually, I like looking at these 3 diagnostics. I like looking at the normal plot of residuals, which immediately we see that it's not following a straight line. I like looking at the residual versus run, which definitely throws off. But then last but not least is I like looking at this box-Cox plot. And this is where it says, hey, we really should consider, because of the broad range of response, that the residual versus predicted levels are increasing, which we see on this megaphone pattern. And so therefore, it's not right to just pool variance across from the low to the high level because there's such a huge range in the response, in this case, 8-fold. And so therefore, let's go back based on the box-Cox plot and reanalyze this. And I'm going to use the base 10 log, but it doesn't really matter. Now, when we do that, immediately you see how those near zero effects line up with the 0. And then over here to the right, I'm just going to lasso these effects. And now with the log scale, you're going to see that they're more significant. But what's interesting is this AB interaction. And this AB interaction is significant. Now, when we do the diagnostics afterwards, we then see everything is great in terms of having a lineup of residuals on the normal plot. There's no megaphone pattern on residual versus predicted anymore. And the residual versus runs are within the red line. And we're in the zone on the box cocks. Some people have come back to me and said, Mark, we did the recommended transfer of a log, but it still says to do a log. Should I do a log of the log? And I'm going to say, don't pile the logs up. Just one log is enough. And then in the end, we get this really cool result where if you keep the factor B low, the heat, then there doesn't seem to be any effective oscillation. But when you increase the heat and then change the oscillation, you get this huge increase in the life of the bearing. And that's what saved the company. Now notice how the LSG bar increases at this higher level because variation is not constant. It increases directly with the level of the response. And that's why the log is called for. So you do see this big LSD bar here, and that does encompass the range of results here. And so that actually leaves a little question here. Does the cage actually help? And that's something that took some further investigation to build up some power on that. And they were able to see that, yes, the change to the plastic did help on top of increasing the oscillation and increasing the heat. And so by doing all three, they were able to get a huge increase in their bearing life, almost tenfold, and at a reduced cost. So this was really an awesome result and a great story about the advantage of doing multi-factor testing, right? Versus one factor at a time. So one factor at a time was a complete fail. It was only through multi-factor that it worked. But the interesting little follow-up to this is that it did require a transformation to really explain the results. So in the end, by studying under George Box, Christopher was able to show that they could look at three factors and for the same number of runs to get a power of 4. And usually when I try to sell the multi-factor testing, I explain that whereas you have one factor at a time here, by doing the multi-factor, you're able to get 4 at the high level of A and 4 at the low level of A. And the same thing works on B from top to bottom and C from front to back. To get the same power, you'd have to do 4 at the baseline, 4 at the high level of B, 4 at the high level of C, and 4 at the high level of A for OFAT. So OFAT would take 16 runs to get the same power that the 2 to the K gets you in 8. So the efficiency is much greater, and you might look at it this way: for a given number of runs, if you're doing 8 runs, you could either just look at one factor with 4 each, or get 2 more additional factors for free. And of course, that's the key, is knowing that 2 factors interact. So that's my little story of how you have what looks to be an outlier, but it's false. So how many people seeing this, just to make sure you're with me, would be more convinced that it's worth doing multi-factor testing than doing OFAT, one factor at a time? Give me the hands to just affirm that this is a pretty good story. And so if you ever present this, if you want to tell the rest of the story, then you would have to mention that it actually analyzes in the log scale just perfectly. If we don't do the log scale, then it seems like that those might have been outliers. Maybe you didn't realize that. Okay. So I have one other case that I'm going to show you, and I'm not, trying to make this too complicated. And the other case is where people miss an outlier. And this is a real story. A fellow named Dave took a class from Statties, our experiment design made easy, and he learned about two-level factorial design. So he went back to his manufacturing site that made these aluminum disk drive housings through a casting process, and he set up a design. I think it was a 2 to the 4 with 16 runs, and he was very careful to do it in random order, which was tremendous. So one day when I was in the office, I felt something, was going on. I just had this feeling, and when I turned around, Dave was standing there behind me, and he had come into the office unannounced, walked in, to where my desk was, and he was just standing there behind me, waiting to see if I would notice him. And so I turned around and I said, Dave, it's great to see you. What's the problem? Because I knew there was something going on. He said, Mark, I said, I want my money back for the class. Really? I said, I thought it was a pretty good class, and, it seems like you're making use of these tools. He said, yes, but look at this half normal plot. There's no effects that are significant, and I'm sure that with the factors I studied, they should have been significant. And I said, Dave, I said, first of all, I'm not giving the money back because you're the engineer. I'm not the engineer. I don't know about die casting. So you're the one that decided what factors to experiment on, and you're the one that determined what levels to set them at, and you're the one that's responsible for how to measure the response. That's not my fault. I said, but hold on a second. I'm going to help you out here. So what we're going to do is we're going to pick at least a couple of these effects that are at the upper end on this effect scale, just to see what happens, because maybe there's an outlier. And lo and behold, there was an outlier. And so I went through this little process. First of all, I picked the effects. I'll show you this on Design Expert in just a minute. But I picked the effects and I said, the three biggest effects are the factor D, the fast shot, the trip, and also the interaction of those two. Does that make sense? And he said, yeah, that does make sense, but they're not standing out on the line like you said they would. I said, hold on a second. Did you look at the residuals? And he said, well, no, I didn't look at the diagnostics. I said, well, look at this. There's one that is way, way off. And I said, Dave, get on the phone. So I said, here's my phone. Call your foreman. So he got on the phone. He called the foreman. And I heard him talking for a while. And finally he gets off. He says, Mark, I apologize. He said, we made a bad mistake, but I didn't know it. It wasn't my fault. But when the foreman did the 16 runs in random order, they forgot one of the runs. And so they felt like I was going to be mad at them about that. So early Monday morning, after the foundry had been shut down over the weekend, we snuck in, me and my crew, and we ran that one experiment. And maybe that might have caused a problem. And I said, yes, so something happened during the startup of the foundry that caused this not to form properly, and it wasn't a good result. So this is easily remedied, Dave. We can just ignore that result and we can see what happens. So let's take a look at it. I've got this die casting, and let's pull that one up. So here's the data, and I'm going to do Control mouse wheel to reduce it down so that it's on your screen. And then it looks like I have several different ways of looking at this as is. And then I copied the data over to a second column, and we'll look at that using the arcsine square root, which really works nice for fraction defect. And then we'll try ignoring the one outlier. So I've got 3 different views of this. By the way, keep an eye out for version 13 of Design Expert. It's going to be coming out with a new feature that allows you to do multiple analyses on one column of response. And I've really been excited about working with that. I don't want to bring it up just yet and show you the demonstration of it because we're still in the beta release. We're coming into second beta release momentarily. But just a heads up is that we've got a really cool new feature coming out with version 13 that will save you the trouble of having to copy over columns like this. So how would we build this up? Let's just take a look at it. I always like to look at how the actual design got built. And so I'll just reproduce it. And you can see here, this is actually 5 factors. I thought maybe there was 4, but there's 5. And this is a nice little structure. I like this one. It's a half fraction of 5 factors. It's a green design, so it should resolve interactions. It's actually a natural minimum run resolution 5. We do have other minimum run possibilities, but this one's a natural for 5 factors. But if you had 6 or more factors, you could use one of these minimum run designs. But this one is perfectly fine. The aliasing is not bad. We've got clear estimates of main effects are aliased only with 4-factor, which we don't show. And the 2-factor interactions are clear of anything that would likely interact. The 3-factor interactions are not an issue. And then here are the names that Dave entered in, units of measure. These are all numeric factors in the levels. And then normally I would do a power calculation, but it's a done deal. So we'll just go ahead and finish that off and recollect the data. And one of the first things I would do is just see if there was a broad range of response, which there is, all the way from almost 0 defect, on a fraction basis to all of it being defective. And I think maybe he made something like 50 parts because they were running probably around 50% defect. So it wasn't too hard to make defective parts. So I think their subgroup size was pretty small. Maybe it was only 20. And then the graph columns will give you an idea of the different individual factors. This is kind of a 1 factor at a time approach. It's not going to reveal interactions. And so now we take a look at the half normal plot, and this is where Dave was quitting and wanting his money back. Nothing was showing up, and so he gave up at this point. So I said, Dave, let's try picking a few of these big ones. Do these make any sense? And he said, yeah, that does actually make sense. Of course, they're not showing up very well in terms of significance, but never mind that, because we can go to the diagnostics. And of course, here we see the story. Now, what's interesting is that there is one off, and I can highlight this, and it definitely is outside of the red lines, but there's no recommended transform here. Later, we'll see that it's a non-power transformation, the arcsine square root, that works in this case. But the first question is, what's going on with this outlier? But before I address the outlier, and this is my advice, is don't immediately throw out an outlier unless there's a special cause, which there was in this case. But even if there is, you might go ahead and try the appropriate transformation first. So I actually went at this and said, well, let's just try for the next iteration the arcsine square root, because that works really well when the response is a proportion, like fraction defect. And that didn't actually help. So then I said, okay, I'm convinced this point is not only a statistical outlier, but also we have a special cause for it. So I'm going to highlight this, and then I'm going to take it out. And you do this by right-clicking and just changing it to ignore. So I'm putting it back to normal, and now I'm ignoring it. So now what happens? Pretty exciting, huh? Look at that. The half normal plot all of a sudden totally clarifies, and this is real data. This actually did happen. And looking at the Pareto chart, it's like, wow, this is unbelievable that we would have missed this if we didn't press ahead and look at the diagnostics. We would have completely missed the whole thing. That there was very significant impacts of this interaction and its parents. And so by ignoring that now and using the arcsine square root, I also recommend, we now end up with, a very good set of residuals that allow us to press ahead and interpret the results. And what they didn't want to do is have low level of B when they had the low level of D. Every other combination was fine, but they just had to be careful not to do this. So that was the answer. By the way, if you really want to show something fun, just to kind of show off a little bit, when you have a strong interaction like this, it actually creates this twisted plane. And you can see that this is a bad combination up here. So that's my story, and it's a true one. So once we found out that there was a weekend shutdown, and then they went back and tried to redo that run, we realized it was not representative of the main block of runs. And therefore, we were able to see a way clear to ignoring it and reanalyzing it. So lesson learned, don't give up if nothing stands out. If you pick one or more of the biggest main effects, and also if they're not high order interactions and they don't make nonsense, then look for outliers. So that would be my advice, my strong advice here. And then you do get this kind of curvy behavior because of the transformation. So that's it then. That's pretty much the story that I wanted to tell. The two different cases are both real life. One was a bearing case where they might have said that there were statistical outliers and thrown all the good data out. On the other hand, is the case where they overlooked a real effect because there was an outlier that killed the whole experiment. So really, the answer is always do diagnostics. And then especially pay attention to the Box-Cox plot. Consider transformations, right, which Box-Cox will recommend. There are some that are not Box-Cox. So it could be, let's say, a non-Box-Cox power law, such as the arcsine square root, was a case where you just have to know something about transformations. So it helps to study, to think, to learn from these examples, and then maybe in the future you won't be overcome by bad data. So in conclusion then, I'd just like to mention that if you're interested in learning about DOE, these books that I'm the primary author of are designed to keep it simple and make it fun. The type of things that I covered in this session are covered in the first book, DOE Simplified, which does talk about diagnostics and transformations. So that would be a good book to pick up. If you're interested in more advanced books, we have one for the response surface methods, or RSM. And then if you're working in formulation, I highly recommend using mixture design. And this book on formulation simplified will cover the different issues, including transformations. We also have some free webinars. We have a crash course for experimenters, and we have a new user intro. Those will be shown on the webinar site. So check into that to see when the next ones are coming up. I think there's one coming up this week, in fact. But check the webinar site, and then you can enroll for free. We do also have training. We've pivoted over to distance learning, which makes it a lot more available worldwide. So take a look at our site and check into these classes. The modern DOE for process optimization is really a good one to start if you're doing process. And then definitely mixture design, as I mentioned, if you're a formulator. We have some specialized training for teams, and you can check into that by contacting our workshops at states.com. So that concludes my presentation. I want to thank you for attending. I have about 15 minutes here till the top of the hour. So either feel free to log off if you like, and then if you want to send me a question by email, you've got my email here. Or if you want to stay on and put your hand up, I'll take your microphone and put it on live if you want to ask a question. Okay, Greg Alexander has got a question. Greg, let me put you on mic. You're self-muted. If you want to take off mute and go ahead and weigh in with the question, feel free. If not, that's fine too. And let's see if anybody else has a hand up. Jeb, I don't know if you have a question. I'm going to take you off, and you're now on live mic, so go ahead and ask if you have something. Okay. Okay. We've got an actual question that's been asked here. Okay, so I'm going to go back over chat now. If you want to ignore an outlier in Design Expert, what do you put in as a response? Rob is asking the question. Okay, and thanks for the answer. Yeah, so the answer I think I showed you in the example is that you can leave the number in, which is really cool, and just do the ignore temporarily. So I highly recommend keeping the number. In the past, we would have actually deleted out the number and dealt with it that way. Okay, why again was arcsine square root your first go-to transformation and not something else? Well, Joe, it's one of those things that is probably answered best by just saying, just because the arcsine square root turns out to be very effective for stabilizing variance near the boundary levels. And so this has been discovered, more through empirical methods that it'll take a situation where you hit these boundaries at 100% off grade or a value of 1, and you hit the boundaries at 0 where there's no off grade, and then the variance starts to change quite rapidly. But by creating a transform like the arcsine square root, you kind of square the whole variance off so that it is fairly stable, very close to the value of 1 and very close on the value of 0. There are actually two types of transformations that are used that are not the power law, and one of them is the arcsine square root, which I covered, but the other one is called a logit. The logit works in a similar manner, but it works really well when you have a bounded response, not just 0 to 1, but any bounded response. And it actually, this logit works pretty well for yield when the values are from 0 to 100. And I would use this quite a bit in some of my work as a chemical engineer on natural vitamin E yields. I was able to get the yields increased from really near 50% all the way up to near 100. And near 100, the values were kind of piling up and couldn't change a whole lot. So the logit actually worked pretty well for that. So those are two non-power laws. Well, thanks, Rob, about the books that you've read, the first two. I appreciate the compliment on the simplified books. And as far as the data that requires arcsine square root, I would always apply it to the fraction defects case of 0 to 1. Manpreet was asking that. What would be the most number of outliers that can be ignored? Ramez is asking. That one is a good question. I would just hazard a guess to say that if you had 2 outliers, then I would be careful to ignore more than 2. And even with 2, I would only ignore the one that has the highest Cook's distance. So that if I was actually in the case of the well, which I'll bring up again and reopen that, I'm sorry, going for the bearings. In the case of the bearings, if I was really believing that there were outliers, then what I would do is I would take those outliers and I would create a view of it using Cook's distance, and I would see if one of them is a little higher than the other. I mean, they're both pretty high, but I would just ignore one at a time and see if after ignoring the one, the second one goes away. But I think if there's more than 2 outliers, that might be off. And that kind of leads into the Cook's question from Michael Morrow. I like using Cook's as a tiebreaker if there's multiple outliers. Cook's is actually better than leverage, I think, and I don't like the DF fits and DF betas quite as much because the limits on those are a little bit flaky. DF betas could be useful if you really drilled down deep and you thought one of the factors was way off on the levels, like the catalyst was so low for the axial low point on the central composite. DF betas could be used, but I would say Cook's distance would be the next go-to after the normal plot of residuals. the residual versus predicted, and the box Cox. If you have multiple outliers, then I would use Cook's and see which outlier has the biggest overall influence, which includes both the leverage and the distance that is off. And Leonard, it's good to see a question from you. Everything seems fine, except that there's a significant lack of fit, even though you have goodness of fit stats, you know, like the adequate precision, things like that. Could this be due to replications being too close? And yes, I mean, I oftentimes see false outliers, false lack of fit, and lots of other things that are really a reflection of the fact that the replicates are the standard condition and they're being set, you know, by the chemist, for example, to get the same result every time. They bias the results so that there's very little pure error because that's what they're taught to do. So I would always be suspicious if there's a significant lack of fit and you look at the pure error and it looks like it's really, really low compared to what you normally would expect. So yeah, I think that's probably a good comment. Okay, well, that brings me close enough to the end of the hour and I don't have any more chat questions. So I would like to draw this to a close. And again, thank you very much for attending. And I look forward to hearing from people with further questions down the line and working with you down the road on making your DOE successful. And certainly feel free if you see any unusual results to send us your data. That's really the best way to get an answer. Okay, take care, everybody. Bye-bye.